We're now ready to tackle our last lesson of our summer assignment, additional periodic trends. We have just finished talking about electron configuration and making some connections with periodic trends. We're going to talk about other trends, the first being atomic radius. We'll talk about ionization energy, electron affinity, and electronegativity. And we'll be doing so one at a time. So where we left off in the previous lesson was our notepad page 13. We're picking up where it says periodic trends, and let's talk about the trends in terms of the size of the atoms, atomic size. And if we're measuring atoms in terms of how small or how large they are in comparison to one another, we'll first talk about how we measure. We realize that atoms themselves, the way that they are composed, are mostly empty space, that we have to envision this electron area being more like a cloud. It's very difficult to measure the region of an area of probability. So what chemists have then decided is to measure the distance between the nuclei of two like atoms that are bound together. Think of those naturally occurring diatomic molecules. Horses need oats for clear brown eyes. Oxygen is one of those 7. In a diatomic molecule, when one oxygen bonds to another oxygen, it's very readily convenient to measure the distance between the nuclei, where those dense regions inside of an atom can easily be found. Once we measure how far the nuclei are from one another, we simply cut it in half and find the radius of the atom. Atomic radius is defined as 1/2 the distance between the nuclei of two like atoms in a diatomic molecule. The size of the atom from the nucleus to the outer edge of the electron cloud. Now, what are some trends we might discover as we think about periodic trends? This is a nice visual. This visual would be very helpful for you to sketch something similar into your notepad. And let's make some discoveries. Group trends. Describe the group trend as it's related to atomic radius. Groups, of course, go down. Columns are groups. What do you notice about the size of atoms as you go down the same column? Well, I agree. The atoms are getting larger as you go down the same column. Atomic size generally increases as you go down a group on the periodic table. Think about why. Each time we're moving down a column on the periodic table, we're adding energy levels. Additional principal energy levels, another ring around the nucleus filled with electrons. Each time we add an additional energy level, we've created a larger atom. Atoms get bigger as you go down a column. An atomic radii trend. Atomic radii, the size of atoms. Atoms get bigger as you go down a column. Why? Be sure you add that in your notes. Why? They get larger because you're adding additional energy levels. What do you notice about a group trend in terms of atomic radii? Periodic trends along the same row on the periodic table. Tell me what you observe as the periodic trend in the rows going across. I notice, as you do too, that the atoms get smaller going across, reading from left to right. Write that in your notes, that atomic size, the size of atoms, decrease as you move from left to right across a period. Why? That seems bizarre. Let's explain that in terms of drawing a little model here. If I think of element, I'll do lithium's row. Lithium right here. Lithium is number 3, mass number 7. So inside of my nucleus, I have 3 positive protons, 4 neutral neutrons. In my first energy level, I place 2 electrons, and in the second energy level, I place a 3rd electron. We understand to write that better. 1s2, 2s1 would be the electron arrangement in the quantum mechanical model, or the Bohr model, 2s electrons in that first energy level. Notice that 3 protons are attracting in 3 electrons. Compare that to the end of the row. Let's just do fluorine. Same energy level. Fluorine is number 9 with a mass number of 19. Thinking about what's inside the nucleus, I'm packing in more particles, aren't I? I have 9 protons and 10 neutrons packing the nucleus. The nucleus does contain more particles. The 9 electrons would place 2 in the first energy level. I have to get to 9, and 7 more in the second energy level. We now know to write that 1s2, 2s2, 2p5. That second ring truly has sublevels of an S and P sublevel. But more importantly, I can describe the trend. The trend brings me to a term called the effective nuclear charge. Our text uses a symbol, Zeph. The effective nuclear charge. 9 positive protons, 9 negative electrons. The more electrostatic attraction, the more those opposite charges attract each other, the smaller the atom becomes. 9 positives can pull in that second energy level closer and closer and closer to the nucleus. The more positive particles I pack in, the same energy level. Notice lithium has 2 energy levels. Fluorine has 2 energy levels, but fluorine has a greater effective nuclear charge. Effective nuclear charge is described as the ability of a nucleus Thank you. Though I get interrupted by the announcements. The greater the number of protons, the more control, the more ability it has to pull in the opposite charge. That these electrons are getting pulled tighter and tighter and tighter towards the nucleus because there's more positives pulling them in. A lower effective nuclear charge, fewer protons, it has less control over those electrons. There isn't as great of an opposite charge attraction. Atoms get smaller as you go across the row. Fluorine, the smallest atom in this column. Now I know it's hard to see on this diagram, but neon actually, when it fills its outer level, gets a slightly bigger diameter than fluorine. Fluorine, the most active nonmetal, the smallest nonmetal that's active. Cesium, the largest metal, the most active metal. Atoms get bigger as you go down because you're adding energy levels. Atoms decrease in size going from left to right because the effective nuclear charge of the nucleus pulls the electrons closer and closer and closer towards it. That increasing nuclear charge pulls electrons closer to the nucleus. Our book calls that ZF, effective nuclear charge. Let's talk about a second periodic trend, the term ionization energy. Ionization, let's try and kind of think about this root word ion. An ion is a charged atom that results from either losing or gaining an electron. Positive ions are known as cations. Negative ions are known as anions. Ions are charged atoms. Sodium, ion, +1 charge, it's a cation. Chloride, ion, it's a -1 ion. Ions are charged atoms either by losing or gaining an electron. So when we refer to ionization energy, very specific, it wants to measure the amount of energy required to overcome the attraction of the nuclear charge and remove an electron from a gaseous atom. The ease at which electrons are lost. Removing an electron. If it's easy, if that atom wants to give an electron away, very low ionization energy. If an atom does not want to lose an electron, more likely to gain, it would have a very high ionization energy. Ionization energy measures the amount of energy required to rip off an electron from its configuration. Now remember, electrons are being held in place by their nucleus. Just from referring to this other picture, how likely is fluorine going to want to lose an electron? If anything, fluorine wants to gain an electron to become like a noble gas. Compare that to lithium up above. How likely is lithium going to want to lose an electron? Well, very likely. Lithium wants to become a +1 charge. When lithium readily loses one valence electron, it has a very low ionization energy. Fluorine, who no way, shape, or form wants to lose an electron, would have a significantly higher ionization energy. How much energy it takes to remove an electron from an atom in its gaseous form is called the ionization energy. In my own head, I think, how easy is it to rip off an electron from an atom? Metals want to lose. Metals have a periodic trend of very low ionization energy. Nonmetals, well, they don't want to lose electrons. They want to gain to become negative. The nonmetals have very high ionization energies. Now, in terms of ionization energy, the first removal of an electron is known as the first ionization energy. The second ionization energy would be taking off a second electron, and so forth. What we notice is, in terms of a trend of ionization energy, we have a group trend. Let's be sure, pause if you need to record these. First ionization energy, removal of the first electron. Second ionization energy, taking off a second electron. We could talk third ionization, removal of a third electron, and so forth, removing an electron. Let's talk about the trends. In terms of a group trend, the first ionization energy generally decreases as you move down a group on the periodic table. As I go down a group on the periodic table, ionization energy decreases. I'm going to put up a slide. As I go down a group, ionization energy generally decreases. It is easier to remove an electron as you go down a column, because the outer electron is farther away from the nucleus. As atoms get bigger going down a column, think about it. Here's the outermost electron. There's the nucleus. Here's the outermost electron. There's the nucleus. The outermost electron. There's the nucleus. The nucleus loses control of that outer electron. This is a term we'll call the shielding effect. This outer electron of cesium is so far away from the nucleus, it is being shielded by all those inner energy levels. Every time we add an energy level, we're shielding the outer orbitals from the nucleus. And if that nucleus is positive, this outer electron being negative, if I take away its ability to attract, it's easier to remove that electron. The shielding effect. Lithium This outer electron is much closer to the nucleus. It has very low shielding effect. Cesium's outermost electron is much more shielded from the nucleus, therefore easily ripped off. Ionization energy decreases as you go down a group. That's the same for any group. Because the electrons get farther and farther and farther away from the nucleus, they're more shielded from the effective nuclear charge and therefore much more readily removed. I wrote that in this direction. Because the size of atoms increases, the outermost electron is farther away from the nucleus and will be more easily removed. The farther out that valence electron, the more shielded it is from the effective nuclear charge. What about a period trend? Ionization energy, the ease at which we lose electrons. If we're thinking about rows going across our periodic table, the periodic trend are the rows going across. For representative elements, the first ionization energy increases as you move from left to right across the period. Remember, because the atoms get smaller as you move from left to right, it becomes increasingly more difficult to remove an electron. As we move across a row from left to right, the atoms become smaller. The smaller the atom, the more effective nuclear charge is going on. The greater the tightness between the electrons and positive protons in the nucleus. Couldn't spit that out. When atoms get smaller, they hold on to their electrons much more tightly. It's much more difficult to remove an electron from fluorine, very high ionization energy. Lithium very readily loses an electron, a very low ionization energy. Because atoms get bigger going down, the ionization energy decreases. Because atoms get smaller going across, they increase in ionization energy. The ease at which we remove electrons from an atom's configuration is known as ionization energy. Hydrogen-helium, period 1, an increase in ionization energy. Lithium, beryllium, boron, carbon, neon, oxygen, fluorine, neon. This is the period 2. A general trend, ionization energy generally increases from left to right. And it's the same trend. Generally speaking, from left to right, across the same row, ionization energy increases due to the atoms becoming smaller and smaller. Trends in ionic size. The size of ions. Top of page 14 in our notes. When atoms of metallic elements have low ionization energies, they will form positive ions easily. Metals become positive. By contrast, the atoms of non-metallic elements readily form negative ions. Nonmetals become negative. Metals are positive. Nonmetals become negative. When metals lose electrons to become positive, nonmetals gain electrons to become negative. What happens to the size of atoms when they lose or gain electrons? Let's talk about the trends. Positive ions are always smaller than the neutral atoms from which they form. Let's take a peek why. Let's just do a Bohr model. Let's do sodium. and I'll just do a Bohr model. Sodium's number 20, or excuse me, mass number 23, atomic number 11. Of 11 positive protons, 12 neutral neutrons, and we would go 2, 8, 1. Now it's an old planetary model. I know I would go 1s2, 2s2, 2p6, 3s1. When a metal loses an electron, and that's what we're doing, it loses that electron. To become positive, it's like erasing an entire energy level. Ions are smaller than their parent atom. Positive ions are smaller than their parent atom because we lose entire energy levels. Their outermost shell is completely lost. Ions, positive ions, are always smaller than their parent atom. Let's do the opposite trend. Negative ions are always larger than their neutral atoms from which they form. Let's take a simple fluorine. Fluorine with 9 positive protons, 10 neutral neutrons. The parent atom would arrange that as 2 electrons in the first energy level, 7 more in the second energy level. 1s2, 2s2, 2p5. If I take in an extra electron, which it wants to do to fill its outer shell, it goes from 7 to 8 electrons. It's gaining an electron. But notice what happens. 9 positive protons, 10 negative electrons. The effective nuclear charge is less. Adding negative charges to the same number of positives makes it a little bit more difficult to pull in that outermost shell. Because I add in an extra electron, that makes the cloud a little bit bigger. Negative ions are larger than their parent atom because the effective nuclear attraction is less for an increased number of electrons. Adding in electrons makes the atom get bigger. Losing electrons makes the atom get smaller. Positive ions are formed when electrons are lost. Negative ions are formed when electrons are gained. The last of our periodic trends discussed in this section is called electronegativity. Electronegativity is the tendency for the atoms of the element to attract electrons when they chemically combine with atoms of other elements. Electronegativity. How easy is it for an atom to pull an electron towards itself? Electronegativity. The measurement of pulling electrons towards itself. Electronegativity, the tendency for atoms of an element to attract electrons towards itself. In a chemically bound compound, atoms don't necessarily always share electrons equally. When they do so, we set up what's called a polar bond. Trying to pull up a table here. Here is a table from our text. This is last year's textbook. Electronegativity values, again, we defined it to be the tendency for an atom of an element to attract electrons that are chemically combined with another element. They're actually calculated values expressed from arbitrary units, assigning fluorine the highest value. Fluorine is assigned a value of 4.0. Cesium, the least electronegative element, is assigned a value of 0.7. Fluorine, the most electronegative element. Cesium, the least electronegative element. Let's suppose, and I'm just going to jot a note in my text here, I know I'm going to write in my book. Let's suppose I have a bond from a molecule HF. A little Lewis dot structure coming up more again in future lessons in chemistry. This is called a covalent bond. The covalent bond means that these are sharing a pair of electrons, but it doesn't mean that they're being shared equally. Fluorine assigned a value of 4.0. Hydrogen assigned a value of 2.1. The difference between fluorine 4.0 and 2.1, the difference is 1.9. That's telling us that this bond is favoring the pull towards fluorine. Hydrogen is left a little bit positive. Fluorine is left a little bit negative. The electronegativity difference indicates that we have indeed a covalent bond, and it is polar. I'm saying words on purpose that might be brand new, but the purpose is seeding a future lesson so that when we get that far, the words at least might sound familiar. It's not expected to have these words mastered. I'm just sprinkling a new lesson here for future use. Fluorine is the strongest of strong nonmetals, pulling electrons towards itself. Cesium's the strongest of strong metals, the most active. The most active metal, bottom left. The most active nonmetal, top right. And you'll see the periodic trends generally will increase. Like you'll always be pointing down and you'll be pointing across as you think about periodic trends. Electronegativity is a numbering system that indicates the strength of atoms to pull electrons towards itself in a bond. The stronger the element is, the higher its value. Note that cesium is the least electronegative element, and fluorine, which has a very strong tendency to attract electrons when it's chemically bonded, is assigned the highest electronegativity value. Electronegativity decreases as you go down a group. Electronegativity increases from left to right. The tendency for atoms of the element to attract electrons when chemically combined is known as electronegativity. The electronegativity trend simply shows lowest value, down bottom left, highest value, top right. Lowest electronegativity, highest electronegativity. That general trend of pointing up. The larger the atom down here, the smaller atoms up here. The electronegativity of cesium, we saw in our chart, 0.7. The electronegativity of fluorine, 4.0. The smallest number belongs to cesium, the least electronegative element. Fluorine assigned the highest number, a value of 4.0. This will allow us to predict the type of bonding that can exist between atoms and compounds and define that as either ionic, which we've learned is electron transfer, or covalent, which we've learned is sharing of electrons. This allows me to seed the very next unit we get to in AP Chemistry, the bonding chapter. So that's coming up in our class coming in the fall. So the summary of our periodic trends has been found in our notes, and what this is referring to is our test-taking tool page has done that for us. If you have this page, I'll just kind of say that better. There's no need to summarize as the note pack is asking you to do. I will let you not do that here as long as you've got a printed copy of the summary in front of you on our test-taking tool page. We said atomic radius increases. Atoms get bigger as you go down, smaller as you go across. Ionization energy, the ease of losing electrons. Electronegativity, pulling electrons towards yourself in a chemical bond. Atoms get bigger going down. Atoms lose electrons easier when you go down. Atoms do not want to pull electrons towards themselves as you go down, so you're looking at the lowest electronegativity, highest top right. Atomic radius, ionization energy, and electronegativity were the three periodic trends discussed in this section. The other periodic trend we talked about was really just the electron arrangement of the valence shell. Pause the video here and take a peek at your section review. When you've finished this, start the video again and check your work.